In the context of acids and bases, now what we're going to do is take a look at a really awesome chemical in our world, and that is water. Water can function both as an acid or a base, depending on what it's surrounded by. And so we have a word for that when it can do both. We call this an amphoteric substance. So water can be both. That amph is a prefix that means both. So let's take a look at what we've seen so far. So we have acids with a hydrogen out in front. We know acids are hydrogen donors. So here's my acid. Now look at the water here. It's accepting a proton, right? And if we accept a proton, that means it's acting as a base, yeah? Because this HCl is an acid, I get my usual hydronium as a product here, but here my water is acting as a base. Now look over here at ammonia. So here is a nitrogen, so that's a hint that it's going to be basic. So this is a base. Well, we know bases accept protons. So I'm going to send an H plus over to that base. And now look at what water's doing. Now water's giving an H away. So now water's acting as an acid. Notice acid and base, base and acid. I always have to have both, so one can give and one can take. And just something else to keep with our patterns, I get a hydroxide at the end of a base reaction, right? So let's talk about water. It can be both an acid and a base, right? So around acids, water is a base or a proton donor. And over here around bases, we could say that water is an acid, or instead, over here, a base is a proton acceptor, right? So around acids, which donate, a base is ready to accept. Around bases, which accept, water is a proton donor. I use a little analogy for this with money. So if I was around Bill Gates, if Joanna Hahn is the water, if I'm around Bill Gates, then I'm definitely a money acceptor. But if I'm around my kids instead, then Joanna Hahn is a money donor. So I'm like the richest person in the world, in their world. So if I'm around the right person, I'm an acceptor. If I'm around a different person, I'm a donor. And water works the same way, just depending on what peers it's around. So let's go a little further with water. Water's amphoteric. It can be an acid or a base, but truly we find water right in the middle of our pH scale here, right? And I'm going to use purple because purple's in between the pink and the blue. And let me just, before we jump to that, fill in a similarity here to say that water is always willing to help. So water donates or accepts protons as needed. We could say that water is neutral, right? It doesn't have a bias towards one or the other. And that's what I see here with a pH of 7. So where does this pH come from? We're going to look at that for a minute here. And let's consider another big word, the autoionization of water. So autoionization, automatic, right? And then ionization is forming ions. So it turns out that water actually automatically forms some ions. Just a few, not a lot, but it forms some ions. So here's kind of a crazy reaction. So if we take water and we add it to another water, it's obviously not a strong or weak reaction. It's very neutral. So I've got these equilibrium arrows here. But one water can wake up and say, I feel acidic today. The other one says, I wake up and I feel basic today. So the acid water donates, not that they wake up and feel something, it's more a flip of a coin, but this water would donate a proton to this water. And as a result, I get hydronium ions and hydroxide ions. Yeah, so hydronium and hydroxide. And now I'm like, that water just acted like an acid and it acted like a base, which is kind of crazy. So what I end up with is I have equal quantities of these two ions, right? So I have equal and tiny concentrations of hydronium and hydroxide ions. So concentration of hydronium is equal to the concentration of hydroxide. Because they're equal, that means that this is also considered a neutral solution, which makes sense, right? We think of water being neutral. And if I look at the numbers for these concentrations, if I measure them, this is going to be 1 × 10⁻⁷ molarity of acid, which is tiny, 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 right? If you move that decimal over, and it has to be exactly the same for the hydroxide. So again, a tiny concentration, but they're equal to each other. Now something should maybe jump out at you. See this 7? And then see this 7 here? Those powers or exponents of 10 are going to be our powers of hydrogen over here on our pH scale. So we measure the concentration of H+, or that's the same as hydronium, right? So we measure those concentrations as pH. And that came from French. They're not exactly all in agreement about what the P stands for, but we can use it as the power of hydrogen. And so we're looking at exponents here. So pH, the formula for it is -log times the concentration of H+. And we're looking here, right, at the power of hydrogen, and here's that hydrogen concentration. Matches up with this proton concentration here. If I know the concentration here of my hydronium in water, this would be the -log of 1 × 10⁻⁷ molarity. Remember that a log and a 10 raised up to a power, those are inverse operations, so they cancel each other out. So all I'm left with is negative times -7. Opposite charges multiply and become positive. And so from that, I get, all on paper here, my pH is 7. So it's the exponent with the charge flipped, essentially here. And so we can eyeball a lot of our pHs just by looking at the exponent and changing the sign. We know where we are on our pH scale. And for water, which has equal amounts of protons and hydroxides, I find myself right in the middle with a pH of 7. So on the next page, we will talk a little more about those pHs, and then on the following page, we'll calculate some of those.